First, let me write down the syllabus first, then we can discuss in detail. Okay. So in this, actually what we are going to discuss is rectilinear motion. And this is also called as simple harmonic motion. And then motion in a plane and projectiles. Projectiles, the constrained motion, work and energy, conservation of energy, Kepler's laws, orbits under central forces, and then friction. So this is the total syllabus of this dynamics, right? So in this, right? So first of all, actually, let me go through one by one. So rectilinear motion and simple harmonic motion. There actually what we are going to discuss is, so if a particle is traveling in a straight line, for example, if I throw this chalk piece like this, then it is going exactly in this direction vertically above in a straight line, and it is coming back on the same straight line downwards. That means, let us say if we want to analyze any particular motion, right, there are maximum of 3 different possible ways we can think of. So one way is the particle moving in a straight line. So this is one way, that is the constraint. So that is the rectilinear motion and the simple harmonic motion both comes under the same category. That means if this chalk piece is thrown like this, it will go in a straight line, it will come back in a straight line. Suppose if I take one more case, there is a spring like this, and then there is a mass that is attached to the spring. Then if you drag this spring like this and leave it, then it will try to oscillate in a straight line motion like this. This is also a straight line motion. That means any straight line motion is called as a rectilinear motion. So one of the example of the rectilinear motion is the simple harmonic motion, right? So if the particle is moving in a straight line like this, this is also a rectilinear motion. If the particle is moving forward and backward, this is also a rectilinear motion. But one subcategory of that rectilinear motion is this simple harmonic motion. Got it? So that means a particle traveling in a straight line we are going to analyze. So that is one-dimensional motion analogy. Right? So there actually what we are going to discuss is, that is the rectilinear motion and the simple harmonic motion. So these two are the important aspects actually we are going to discuss in case of one-dimensional motion. And immediately we can think of the two-dimensional motion. So two-dimensional motion is any generic motion. Yeah, just a minute. Sorry. So this is actually one-dimensional motion. So immediately we can think of two-dimensional and three-dimensional, right? So two-dimensional motion is nothing but any generic motion which is on a plane is called a two-dimensional motion. For example, if I throw this chalk piece like this, then actually this chalk piece will travel in this direction. That means if you notice at any instant of this particular chalk piece, there is some associated height and there is a associated length from the point of displacement. That means if you throw this chalk piece like this, so you have to count both the height it is going to travel, at the same time the displacement from the starting point to this point. So two different aspects you have to notice, and that kind of motion is called the motion in a plane or a 2D motion. So this is motion in a plane. So in motion in plane, right, so there are actually multiple ways we can think of. So one example of this motion in plane is the projectiles. Can somebody tell me what is the other example of this motion in a plane? Give me some other example. So motion in a circle or circular motion. Motion in some random fashion on a plane is called a planar motion or two-dimensional motion, right? So that means if a particle is traveling, suppose actually Earth is traveling around the sun in an elliptical orbit, that is also a motion in a plane. So a particle traveling in a parabolic path, that is also a motion in a plane. So any two-dimensional shape you can think of for a motion in a plane. So to analyze this aspect, so you might have analyzed these projectiles already at +2 standard. Now actually we are going a little deeper into that. So we are using the coordinate system. So actually earlier we were using only the Cartesian coordinate system. Now actually we will go a little deeper and then try to analyze with the help of polar coordinate system, which is much more convenient for certain types of motion like circular motion. So that is the extra thing actually what we are going to do when compared to the +2 standard, right? So that is the motion in a plane. This is very, very interesting topic you can think of. And then even in this Kepler's laws also comes under the motion in a plane only, because actually, so Kepler's laws actually he laid out some of the rules. So those rules actually, so every planet tries to rotate around the sun in an elliptical orbit as sun as the one of the focus of the ellipse. So that is one of the Kepler's principle. Now if you notice, the particle or the Earth is trying to rotate around the sun in an elliptical orbit. That means that is again a motion in a plane. And then there are some constraints that are associated on it. So that's what is called the constrained motion. That means, for example, if I give one more example like this, suppose if I tie up a thread for this chalk piece and then try to hold the thread like this and rotate, that means it will try to rotate in a circular path again, right? Now, there actually I am constraining that particular particle to rotate only in the circular fashion. That means I am putting a condition on the path. Suppose if I take one more shape like this, suppose actually there is a bowl like this. On this bowl actually I throw one ball. Now this ball actually I have given a motion like this. Now actually though I have given in this direction, it will try to go in this particular path, but it won't go this way. I am constraining this ball to go along this particular line. And this is what is called the constrained motion. So usually this constrained motion, right, we will be applying on 2D. So it's not that actually we can't apply on 3D. We can even apply on 3D also. But as per our scope of discussion, it is only applied only for the 2D shapes. So this is the constrained motion where you are constraining the particle to move only in a specific direction, right? So in that, right, so constrained motion, there is something called the central force also is one of the constraint. So as per the gravitational rules of Newton's, right, if there are any two different bodies having certain mass, then for example, if I take these two chalk pieces together, if I keep these two chalk pieces like this, then actually there will be an attractive force between these two masses. But that attractive force is very negligible in case of normal masses. So, because there is something called gravitational constant. So that is the force between two different masses is proportional to mass of the two bodies and inversely proportional to the square of the distance between these two. This is as if like the Coulomb's law. And then if you replace this proportionality with some constant which we call as the gravitational constant, g into m1 m2 by r square, where this g is of the order of 10 power minus 11. So if it is of order of 10 power minus 11, then you can simply neglect for smaller masses. But what if the mass is compared to 10 power minus 9? For example, if you take the mass of the Earth, so that will be somewhere more than this 10 power 11. That means you have to consider that mass as well. When we compare the force between the two masses, if you compare the mass of the Earth and mass of the Sun, there will be a considerable amount of masses that are there. Then obviously there will be a force of attraction between those two, because the Newton's law says that every random masses can have always an attractive force between them, but the order of the magnitude may be less or may be more depending upon the size of the mass, right? So here actually, in case of these huge masses like Earth or any planet, right? So there actually we have to consider the force between them. Now there exactly the discussion of the central forces comes into picture. So central force, by definition, what it says is, suppose if I take Sun at this particular point, and then Earth is moving an elliptical orbit like this, and this is the place actually where the Sun is located, then obviously, as per the Newton's law, there will be an associated force between these two. That means the force is always in the line joining the two masses. So this is the line of action of the force when the mass is presented like this. Now the same mass is moved to this location, then the force of attraction between these two in this particular line. Suppose if this particular mass is moved to this location, the force of attraction is on this particular line. If the mass is located at this location, the force is on this line. Now if you notice, this Earth is continuously moving, but the line of action of the force always passes through a single point called the focus of this particular ellipse. That means this is constrained to attract in a direction which is always passes through the single point, which we call as the constrained motion, which we call as the central force. So central force meaning the line of action of the force always passes through a fixed point, and that is what is called the constrained motion. So in the constrained motion, right, so this Earth is moving in an elliptical orbit just because of the reason of this central force action. So this is what we are going to discuss in case of central forces. So one of the particular case of the central force is nothing but the Kepler's law there, where the force between the two masses is inversely proportional to the square of the distance between these two. That means F is directly proportional to 1 by r square. So this always leads to a central force. This always leads to a central force. So because of this only, we came up with the conclusions of this Kepler's law. Kepler concluded that based on this, there are certain properties that are associated for the central forces. Those properties are, that is, T square is directly proportional to R cube, that is one. And there is one more, that is every particle which is subjected to the central force will always tries to rotate in a path which passes through the central force. So that is one constraint. And one more important aspect is F is directly proportional to 1 by r square will always leads to a rotation which is always planar in nature. For example, if I take this planet, right, so this planet will try to rotate an elliptical orbit, but it won't be an ellipsoid. Got it? So it will try to rotate an elliptical orbit, but it won't be an ellipsoid. What it means for us? See this. This is the chalk piece. Let us say this is the sun. Now this particular particle, which is nothing but the Earth is trying to rotate an elliptical orbit like this. So this is an elliptical orbit, but this ellipse can be this way also, right? And this ellipse can be this way also. So once it can travel like this, and another way it can travel like this, and another way it can travel one more ellipse like this. That means if you cut any particular section, right, so that is going to show an ellipse, right? But in reality, it is not happening. It is trying to rotate in a fixed elliptical orbit always. That means, so if it starts rotating in an elliptical orbit which is on the exact plane like this, and it will always tries to rotate only in that particular path, but it won't divert from there to take one more elliptical path like this. And this is the condition for the Kepler's law. This condition is just because of the reason or the fundamental property of this central forces. So this is one derivation what Kepler has proved to say that the planet is always rotating in an elliptical orbit. So that is on a plane always, right? So these kind of things actually which we are going to conclude based on the force, whether it is proportional to 1 by r square or 1 by r cube or 1 by r power 4, anything like that. So here actually we are going to discuss the law of force which will describe this particular path. So those things we are going to discuss. The central forces together with the planar motion will come under the category of this Kepler's laws. Got it? So this is about the Kepler's law. So orbits under central forces. And then so energy and conservation of energy. So energy, as and when, right, so we do certain work, then there will always be an associated energy with it, as long as there is a restoring force on that. That means if I lift this chalk piece, obviously there will be a force of attraction towards the ground. That means I am applying my force against the restoring force of this particular chalk piece towards the ground. That means I am trying to push it like this. So I have applied an external force. Then it has got the ability to go back to the ground. This ability is called the energy. When I am doing the work or when I am lifting this chalk piece, right, I say that I feel that I have done some work, right? I have done something valuable. So that valuable is nothing but stored in the form of energy on this particular chalk piece, right? So this is what is called the potential energy, right? When the particle is moving, so this energy actually whatever we have got because of the movement from one location to another location by virtue of its position is called the potential energy. Suppose if there is an associated velocity to this particular chalk piece, then when this chalk piece hits our body, automatically we feel some sensitivity or actually we feel some force on it. That means because there is an associated energy on this particular chalk piece that is trying to discharge to my body, during the translation actually I feel that there is some heat on my particular body, right? So this energy by virtue of its velocity is called the kinetic energy. So those two energies for any moving particles will always be there, and those energies actually we are going to calculate and try to correlate it, and then from there actually we try to conclude that the law of conservation of energy, which says that energy can never be created nor destroyed. That means whatever the energy we give it, this is going to be converted into kinetic energy or into the form of potential energy. The sum of the energies together will always lead to a fixed quantity, right? So this is what is the conservation of energy, right? So if I say that the conservation of energy, that means when energy can never be created, cannot be destroyed, right? In that case, from where actually we have to get this energy? Somewhere we have to get it, right? Then only we can say that we cannot be destroyed or we cannot create it. If we are not creating, obviously somewhere we have to get it, right? From where we can get it? Where can we get this energy? Because actually no human can create the energy. Can somebody give me the answer? So no human can create the energy. Solar is one form of energy. Any other form of energy? Any other form of energy? So gravitational energy, chemical energy, right? So if you notice, the source of all the forms of energy is only from the nature. So energy can't be created, but already the energy is present in some or the other form in the nature. So we are trying to reuse that energy, converting from one form to another form. So all our applications are only to convert the existing energy that is there in the society, right? So that energy actually what we are going to use is we are trying to convert that one form to another form and then try to make use of that while it is converting from one form to another form. So this is what we are going to do it always, right? So energy can't be created. So we have to extract from the nature, no other way. So as it is coming only from the nature, so these resources are obviously it will be limited. So obviously everyone actually, so who has the energy, so like actually who want the energy, right? They will try to capture that energy obviously, right? So in this way, like actually the world wars are actually the main reason of any particular world war, actually any war between two different countries is always just because of this energy. Because this energy can't be created. We have to extract from the nature. That's exactly the reason for all the wars, right? So this energy, that is nothing but the conservation of energy. Energy can't be created or not be destroyed also. So we have to use or we have to make use of this energy from the nature, right? So like this actually all these aspects what we are going to discuss in case of the dynamics topic, right? It is just making use of this energy to convert into different particular forms. And when we are converting into these forms, right, it is going to show some effects. That's what is the kinetic energy or the potential energy or the movement of the body or establishing a force. All these things are the effects of these energies. So these are the things actually what we are going to study in case of dynamics topic. Now actually in case of statics, if you notice, if there is a force, right? So when the forces are there and all are balanced forces, then actually there is no movement at all. But now what we are going to deal is, if the forces are not balanced, obviously there will be an associated movement. When there is a movement, what kind of movement it is going to be, and what is the reason behind the movement, and what are the effects of the movement, all those things actually we are going to study in case of dynamics. Got it? So if there is an effective force, obviously that force will cause some other action on the body. That action is nothing but the movement of the body. So that movement can be in multiple ways. Maybe in one-dimensional motion, or maybe in two-dimensional, or maybe in 3D. So in 3D also, like we have actually a specific topic in vector calculus, that is Serret and Freinet formula is just based on 3D motion of the particle. Serret and Freinet formulas are only for the 3D motion of the body. But here in our statics and dynamics topic, we have only two-dimensional motion and one-dimensional motion, not more than that. So this syllabus is pretty simple, we can easily tackle it. But only thing is, we have to be aware of certain fundamental topics, like very fundamentals of solutions of the differential equations. So not very great level, very fundamental equation, that is d square y by dx square. So I will give you d square y by dx square. We are going to solve. First you note down this, I am going to analyze that. What we have to learn in this particular topic. First you note down this. So to handle this particular topic, right, we have to be aware of only two different differential equations, that is d square x by dt square is equal to 0 or d square x by dt square equal to some constant a, or d square x by dt square may be a function of time, or d square x by dt square is proportional to x. So these are the differential equations actually what we are going to deal in case of dynamics topic. Now actually what is the importance of these topics? Importance of these differential equations. Now if you notice, so we have the fundamental aspect of Newton's laws. First law says that every body tries to stay in its state of rest or of uniform motion unless otherwise it is compelled by an external force. So that first statement what it says is, to have a motion there has to be an associated force. So unless otherwise it is compelled by an external force. That means if there is a block like this, unless otherwise I apply an external force, this won't move from this location to this location, right? Obviously, right? So if I give an external force like this, then only it will try to move from that particular location. This is what is the first law. So and the second law, what it says is, so the force what I have to apply to move this particular body. So I have to quantify that, right? With how much force actually. Suppose, let us say, I have actually a big stone of mass 1 ton, let us say. But I am trying to push it. Obviously, I will not push it. But I have applied force. I should not feel that I have applied the force but it is not moving. Because my force is not sufficient to move that particular mass. Then actually how much force I should apply in that case? So that question comes automatically. So the answer to that question was given by the second law of motion. So that is, what it says is, the force applied is proportional to rate of change of momentum. This is what is the Newton's second law. So how much force I should apply is proportional to the rate of change of momentum. So movement is different and momentum is different. Movement is nothing but torque in case of statics. But momentum is nothing but, it is represented with a letter called P, and this is the product of mass into velocity. So this is what is called the momentum. So the product of mass and velocity. That means, so this momentum is proportional to m and this momentum is proportional to the velocity. That means, so suppose actually if I hit with this chalk piece, right? Obviously you don't feel much of the force, or actually you don't, so it won't pain much. Suppose actually if I take this much size stone and then try to push on a body, somebody, then actually obviously he feels that actually he might have died already, right? So because actually the size of the stone is more, that means the force actually with which it is trying to hit the body is proportional to the mass. Suppose actually if you take bullet mass is almost like 4 grams or 5 grams or maximum 100 grams bullet, right? Now actually this bullet is trying to, suppose if you leave the rifle, right, automatically this bullet will go and then hit the body and go inside, and there also he is dying automatically, right? The reason being the mass is not very big there, but the velocity with which it is traveling is very, very high. So big mass with small velocity will have an equal impact of small mass with very big velocity. So the product of these two will be directly proportional to with what force it is trying to move. So that's what is called the momentum of this particular body. That means it is proportional to both of these things. So P is equal to mv. Now with which actually I have to push is nothing but the rate of change of momentum. Rate of change of momentum. Suppose if I take this particular mass, right? Let us say the mass of this is m, and then this mass is fixed here. If the mass is fixed, then actually the force applied is directly proportional to rate of change of velocity. So m1 v1 minus m2 v2 by t2 minus t1. So this is the rate of change of momentum. Here in this particular case, m1 is equal to m2 is equal to m. Because the same block is trying to move, but initially it was under rest. Now actually I have applied the force. Because of that it started moving. That means actually I have made a change to the velocity of this particular body. Because of the change in the velocity, obviously the momentum is going to change. Initial momentum is 0 because the velocity is 0. That means there is a change of mass is same. It reached to a velocity of v initially when it was a velocity of 0. Within a time of t2 minus t1. So initially if I start with 0 seconds, then actually t minus 0 is the time. So this is mv by t is nothing but the force. This is the force when the body started moving from the rest. Suppose if the mass is keep on increasing or it will keep on reducing, that means there is a change in the mass as well. So in that case, so what we have to do is this f, to be specific, we have to define this as dp by dt, rate of change of momentum. It's not like m into v2 or ma. So ma is one specific case for mass. F is equal to ma is one particular case where the mass is constant for any force. And the 100% accurate is F is equal to dp by dt, which is nothing but the rate of change of momentum. This is what directly coming from the Newton's second law. So with what velocity it is moving, that depends on the mass of the body, at the same time the velocity of the mass of the body, at the same time the force that is applied on the body. Both are actually relevant to each other. That means the rate of change of momentum is directly proportional to F, or rate of change of momentum is nothing but the force I have to apply to move this particular body. So if I have bigger mass, obviously I have to apply more force. If it is a smaller mass but I wanted to move with a high velocity, I have to apply more force. Right? So both are interrelated to each other. So the statement you can straight away take it. Now in this particular case, if the mass is varying, suppose actually take the example of conveyor belt. So there actually the mass is continuously poured on the conveyor belt. Now when the belt is trying to move it, the mass on the conveyor belt is keep on increasing. That means there is a change of mass also along with the velocity. Or sometimes velocity may be constant but mass may be changing. For example, if you take one more, so take a truck lorry. So in that actually you fill up with completely sand, and then there is a leakage at the bottom. Lorry is moving at a velocity which is constant, maybe 60 kilometers per hour, but continuously the sand is coming down onto the road. That means the mass is continuously changing, but the lorry is moving with a constant velocity. So there the velocity is constant, but the mass is different. That means there the force that needs to be applied to the lorry to move is equal to V into m2 minus m1 divided by t. So this is the force I need to by applying there, or t2 minus t1, rate of change of momentum. But all these definitions fits under the single formula, F is equal to dp by dt. So dp by dt is equal to d by dt of mv is equal to m into dv by dt plus v into dm by dt. So this is the complete definition for the force of any particular particle to move. How much force you are applying is equal to this one, where if m is constant, dm by dt is 0, then we have m into dv by dt. Rate of change of velocity is called the acceleration. That's why we replace with m into a in case of force if the mass is constant. If the mass is varying and the velocity is constant, then you can treat as v into dm by dt as the force. If both are changing, then you have to use this complete formula. Got it? Understood? Okay, you can note down this. So from this place, actually how we are coming out to this one, I am going to explain. So this is Newton's second law. Newton's third law, what it says is for every action there will be equal and opposite reaction. So this is what actually we dealt in case of statics. So there the normal reaction is nothing but the direct example of Newton's third law. So here actually we are dealing with only the dynamics part of it. Here actually see this. So we have got F is equal to m into a. Now actually we will define what is this a. Suppose if there is a particle from here to here, it is moving in a straight line path like this. So from point A, it is moved to point B. So when we see, right, we say that the point is displaced from this location to this location. Displaced. That means we are talking about only the locations. We are not worrying about the way it is displaced. That means from A to B, whatever the line you can straight away draw it, or the least distance part. Is called displacement. So this is the displacement. Suppose I can travel from A to B in n number of ways like this. But there is always only one least path will be there. That is a straight line path from here to here. And this least path is called the displacement. And whatever the normal route you take based on your convenience is called the distance. So this path distance is the distance, and this least path distance is called the displacement. Now displacement actually you can always draw starting from one point to the another point in a straight line. That means there will be an associated direction. But for distance we don't have the direction, so you can travel in any. So no specific direction. Hence displacement is a vector. And usually represented with x. And then, so this rate of change of displacement, rate of change meaning it is changing with respect to time, and how fast it is we learn as the velocity. Rate of change of displacement. Rate of change of displacement is called the velocity. That means the velocity is nothing but how fast it is moving from here to here. This displacement. So this is what is called the rate of change of displacement. And the acceleration A is defined as with what velocity it is continuously changing, d square x by dt square or dv by dt. So this is what is called the acceleration A. So accelerate, meaning suppose actually when we are driving the bike, right, we will try to push like this. So we are rotating our accelerator like this. So what we are doing there is we are trying to increase the velocity or decrease the velocity. That means acceleration or deceleration is nothing but changing the velocity, not changing the displacement. So when you are changing the velocity, automatically there will be a change in the displacement also. But the rate of change of displacement will be much more different than when we have the constant velocity. That means this acceleration will be the fundamental quantity for dealing with all the aspects, because this is directly related to the force. So by definition, as per the Newton's second law, what we have given is usually we are going to deal with only the constant mass. So if it is constant mass, then F is directly proportional to A. So force applied is directly proportional to the rate of change of velocity. That means it is directly proportional to the acceleration, because F is directly proportional to m into v2 minus v1 divided by t2 minus t1. So this rate of change of velocity, change in velocity by change in time. So this is what is called F is equal to m into dv by dt. So this dv by dt is called as the acceleration, or A is equal to dv by dt. That means here actually, to come in a serial manner, to have a displacement, you have to apply an external force. That is as per the Newton's first law. And then this force quantity is given by the Newton's second law. But visually, actually what we can see is only the velocity and the displacement. That you can correlate with the help of only the velocity, only with the help of acceleration. So that acceleration and the velocity relation is given by A is equal to dv by dt. And v and displacement relation is given by dx by dt. And acceleration and displacement relation is given by d square x by dt square. So this is how the continuous flow it comes. So you start with force and then try to come to a relation to the displacement. So starting is acceleration and ending is the displacement. But that acceleration is caused by the force. And the force direction and acceleration direction, we always treat as a single direction. It is always same. That means, suppose if there is a force in this direction, then we say that there is an acceleration in this direction, because F is directly proportional to A. If F is a vector, A is also a vector, and F and A are directly the same. That means F is equal to ma. So if A is the acceleration vector and F is the force vector, and this is a scalar multiplication. That means F direction and A direction are always the same. Got it? So here we are coming to a single line analysis first. That means the motion in a straight line. In case of motion in a straight line, we are dealing with only one variable, that is x, which is nothing but the displacement vector. So in any particular direction, if a particle is moving, we are dealing with a one-dimensional geometry there. So there, the rate of change of the rate of change of velocity is nothing but the acceleration is given by d square x by dt square. Now we will come back that d square x by dt square is equal to 0. We mean the acceleration is 0. If the acceleration is 0, then the particle is trying to move with a constant velocity. Why? Because if you integrate this with respect to dt, then dx by dt equal to constant. But we treat this dx by dt as the velocity. So if dx by dt is velocity and velocity is coming out to be a constant. So if the acceleration is 0, then the velocity is going to be a constant value. So this is one case where we straight away deal with the formula, that is displacement by time is nothing but the velocity always. That is valid only in case of constant velocity or 0 acceleration. Now we take the second case. If the acceleration is non-zero but it's a constant, that is usually the case we are going to analyze it. So in case of +2 standard, actually we are going to deal with all the aspects only with this single formula, that is d square x by dt square is equal to a. So there actually this formula was so directly not mentioned, because actually we are already aware of the differential equations a little bit. That's why we are going to deal with the d square x by dt square is equal to a. Now if you integrate it, we are going to get all the four formulas of the straight line motion, which we are going to deal with now. So first you note down this, we are going to integrate this. So d square x by dt square equal to a, which is a constant. If it is a constant, if you integrate it, then dx by dt equal to at plus some constant c. And then dx by dt is called the velocity v. So at t equal to 0, so that is nothing but initially when we start, that is at t equal to 0, let the velocity be u. That means when we start driving the bike, so immediately we will raise the accelerator, right? So there actually, let us imagine that we started with certain velocity already. So that is a magnitude of u. So this u may be 0 or may not be 0, right? So if the initial velocity is 0, at t is equal to 0, then v equal to u 0 plus c. It implies c is equal to u. So v is equal to u plus at. This is one important formula. V is equal to u plus at, where u is the initial velocity, a is the constant acceleration, t is the time. And then if you again integrate this v, which we call as dx by dt, then this is going to be x is equal to ut plus half at square plus some random constant c. Now again, at t equal to 0, when we start the bike, we are at a displacement of 0, because that's where we started already. So when we are started, we count the displacement from that particular point, which we say that x is equal to 0 at t equal to 0. So if you replace that, x is equal to u into 0 plus half a into 0 square plus c, it implies c is equal to 0. So c equal to 0. So if you replace there, x is equal to ut plus half at square. So this is the second important formula. So here actually three different cases we dealt with. One is with constant velocity where the acceleration is 0. In that particular case, we directly write velocity equal to displacement by time. Velocity equal to displacement time in case constant velocity. If the particle is moving with a constant acceleration, then the velocity is going to be continuously changing, because actually it is an acceleration. Acceleration, that too with a constant acceleration. That means you are keep on increasing the velocity. Obviously, if you start versus after 10 seconds of start, the velocity will be completely different. And how much it is going to be? It is as if like v is equal to u plus at. Now if you notice, this is a straight line for us. Y is equal to mx plus c. So here, so this is the initial velocity u, this is the velocity, and this is the time t. So this is the graph. So for at any instant, this height you can write as v is equal to this initial velocity, that is the y-intercept values, plus the slope of this particular one is nothing but a. Acceleration is nothing but dv by, so acceleration is nothing but the slope of this particular one, right? So here u plus v plus, sorry, v is equal to u plus at. This is the velocity at any instant of time. Now when you are keep on increasing the velocity, so the distance that is traveled in the first second versus the distance traveled in the second second is completely different, because the velocity in the first second is different and the velocity in the second second is different. Now how to calculate the displacement? That is going to be given by x is equal to ut plus half at square. So this is the displacement and time relation. Now here, so with this one, right, so if you notice, this is a parabolic shape. So it is as if like, see this, ax plus bx square format, y is equal to. So y is equal to ax plus bx square is always a parabola. Now here, instead of x it is t, instead of y it is x. That is the only difference. Now if you draw the graph of it, this is x and this is t. So this is an xt graph. In case of xt graph, we are going to get the parabola path. So this parabola, so it keeps on increases like this. So x is keep on increasing exponentially with the change in the time. So that means this is a parabolic path. No, it's not the path. This is the parabolic variation of displacement with respect to time. The path is a straight line. Got it? So what we are going to deal in this particular case is, we are dealing with only the straight line motion. The straight line motion, because we have taken only the x with respect to time. This is the only relation. We are not considering the y relation there. So if the particle we are considering is both on x and y direction together, then that is going to be 2D. So this is a single dimensional motion, but displacement time relation is going to be in a parabola, right? And velocity and time relation is going to be a straight line. So this is the relation. So what we are going to deal with. But other formulas actually derived from these two formulas. First you note down this, other formulas also I am going to derive it. So all these things are only the fundamentals. We have not yet started our topic. So all these fundamentals you have to be aware of before starting our topic. So V is equal to U plus AT and S is equal to, or X is equal to UT plus half AT square. Now from this relation, I can write V minus U by A equal to T. So this actually I will replace in this so that I can get a relation between X and V directly. So X is equal to T, if I take out U plus half AT, V minus U by A, U plus A into V minus U by A into 1 by 2. So this A will cancel out, and then this is going to be V minus U by A times of V plus U by 2. So this is V square minus U square divided by 2A is equal to X. So the famous relation of V square minus U square is equal to 2AX, we can get it. Got it? So this is the other relation. Now actually sometimes we are going to deal with the displacement traveled in one particular second. For example, from 10th second to 11th second, how much displacement is traveled? Now there actually when we are normally deal with, right? So we will calculate the displacement traveled till 11th second, and then we will calculate the displacement that is traveled till 10th second, and we will subtract from 11th second to the 10th second, so that actually we can get the displacement that is going to be traveled from 10 to 11. So that is in the nth second, so in the 11th second. So yes, nth second is equal to x n minus x n minus 1. So this is the nth second displacement that is going to be traveled. So this actually xn is nothing but un plus half an square minus u into n minus 1 plus half a into n minus 1 whole square. Right? So this actually we have to simplify it. This is xnth, what we are going to get is u plus a into n minus half. If you simplify this, you are going to arrive at this. Got it? So u plus a into n minus half, where n is the nth second, on which second actually you are trying to calculate the displacement. So this is xnth. If you notice, dimensionally is this formula correct? Can you do a dimensional check on this? Dimensional check meaning left side and right side of the equal to sign, it has to associate with the same fundamental formula. That is, length, mass and time. So these are the fundamental formulas. Now actually x length is nothing but the displacement. But here u is the velocity, right? Is this dimensionally correct? But actually in physics the fundamental rule is that no formula can violate dimension, right? Not only in physics, in every subject. So unless dimensionally it is correct, we cannot treat that equation as a valid equation. So do you think that this is an invalid equation? Because the fundamental physics rule says that every equation has to hold with the dimensional rules. So no equation can exist unless it is satisfied with the dimensional rules. Now here, if you notice carefully, so this is not displacement, x nth. So this subscript actually will make a lot of difference now. So displacement traveled in 1 second. So displacement in 1 second. So again it comes back to the same rules of velocity. So left side is the velocity and right side is also this is velocity and this is also velocity. Got it? So dimensionally this is correct. Got it? Okay, you can note down this. So these are the 4 different formulas we are going to deal in case of straight line motion. So these are the 4 formulas when the acceleration is constant. Suppose if the acceleration is not constant, for example, d square x by dt square is equal to some function of t, then here the acceleration is no more a constant value. This is a function of time. So this is also a one-dimensional motion only. That means any random function of time it can come in. This is again a one-dimensional motion. So this we are going to analyze with the normal calculus by integrating. So once if you integrate it, we are going to get the velocity. So this is velocity is equal to integral f of t dt and displacement x is equal to, so whatever you are going to get, this is v is a function of time. So this is the velocity and acceleration. So velocity and displacement calculations with the help of this function of time. Right? So these are also comes under the category of one-dimensional motion. So the integration is dependent on this particular function. So this function you can integrate it and then finally get the values of v and x in case of the one-dimensional motion. Right? So these are the things only are part of the one-dimensional motion. And in case of one-dimensional motion, if this acceleration d square x by dt square is directly proportional to and opposite to x. This is one particular case where d square x by dt square is equal to minus kx, and this differential equation, if you notice, d square x by dt square plus kx equal to 0. This is any equation satisfies this differential equation is called a simple harmonic motion. So any equation or any particle which is traveling in a path which is satisfied by this differential equation is called a simple harmonic motion. So the fundamental property of this simple harmonic motion is, with respect to a fixed point, it will try to rotate forward and it will try to move forward and backward like this. So it will go towards this direction and then actually it will come back to its initial position and then it will go in the opposite direction. It will try to rotate like this, or it will try to move in this path like this. Now here at every point the fundamental principle there is the force on that particular particle. Suppose actually if I take this particular case, this is the mass of the block, then on the table this mass is present and then there is a spring that is associated, and then actually we drag it till this point and then left it. Now to drag this, right, you have applied some force. Now the restoring force, whatever it is there, the restoring force will always be in the opposite direction the way you have applied the force. That means this spring is dragging towards this direction when you are pushing this direction. So this restoring force is nothing but the force which is in the opposite direction. So this is the restoring force. And obviously we can feel that when you drag more distance, the force will be more, or the restoring force will be more. So when you are keep on moving this, the force that you are going to put it on that particular mass to move a little distance is very, very high when compared to the initial position, obviously. That means the force you are going to apply is proportional to the displacement displaced from this location to the other location. That means F is directly proportional to X. And if you notice, when you are dragging this direction and then it is trying to push back to the opposite direction, that means the direction of the force is always opposite to the displacement. You are moving in the positive X direction, but the displacement, so when you are moving into the positive X direction, the force will be in the negative X direction. If you take the other side, if I take this location, so this will be pushing towards this direction, but this spring will push in the opposite direction. So spring will push in this direction, but the particle is ideally moving towards the left direction. So when the particle is moving left direction, the restoring force will try to push back to the initial position. When you are moving in this direction, the restoring force will drag back. That means if you are moving in the positive direction, the restoring force will be in the negative direction. If you are moving on the negative direction, the restoring force will be in the positive direction. That means the force is always in the form of F is directly proportional to minus X, and the force that you are going to apply is proportional to X also. So hence we got the relation m into d square x by dt square is equal to minus px. P is a constant, and d square x by dt square is equal to minus p by m into x, and this p by m is a constant. So hence d square x by dt square is equal to minus kx is a motion which represents a simple harmonic motion like this. So this solution of this differential equation itself is a separate topic for us. Got it? So if you notice, what we are going to deal is very simple part of the dynamics what we are going to deal. So here one differential equation is equal to one topic of ours. So these two differential equations is rectilinear motion and simple harmonic motion together we are going to solve it. Now based on the central force equation, that is F is directly proportional to 1 by r power n. This is the central force equation. So this equation we are going to deal with the help of polar coordinate systems there. So we are go a little deeper into this particular equation will be the solutions for many other central force equations, including the Kepler's laws. Got it? If n equal to t, n equal to 2, then we treat that as a separate topic called the Kepler's laws. Got it? So you have got a fair idea how we are going to deal this dynamics topic and what are all the things that we are going to learn in case of dynamics. So in statics actually there are forces but no movement. But here there is a force, and because of that the particle is moving. So if it is moving, then how it is going to move? Is it going in one dimension or two dimension? Is it constrained or actually any other constraint established or no? So all those things actually we are going to analyze in this particular case. Got it? So it won't be tough, it will be straightforward and easier methods only. So you have to be aware of these fundamentals what we have discussed today. Clear? Any questions on this? Any questions? So with this actually I would like to stop the class for today. So in the next topic actually we are going to start with rectilinear motion. So with the formulas whatever we have derived, we assume that these are known, and from there actually we will take it up further. So till then, thank you. Good night.